atomic structure and atomic theory, and then followed by an introduction to the periodic table of the elements. That's the topics we're going to cover in this lesson. We've got a fair amount of ground to cover. We're going to start with some of the early fathers in modern atomic theory. We're going to go through isotope symbols and how to identify the atomic number and the mass number. We'll talk about isotopes themselves and how you calculate the atomic mass, knowing some of those individual isotopes and their relative abundances. We'll talk about the subatomic particles, protons, neutrons, electrons, and then we'll finish this lesson off by taking a little bit of a cursory look at the periodic table and how we divide up some of the elements and how we look at the columns as groups and the rows as periods and why it's called the periodic table. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. This is the first lesson in the second chapter of my new general chemistry playlist. I'm releasing these lessons weekly throughout the school year, so if you want to be notified every time I post one, subscribe to the channel and click the bell notification. Let's get into this. So a little bit of history to start with here. And we've got 4 early fathers of atomic theory that all made their contributions. And you got to know just a little bit of what contribution each of them made. Now we'll start with Dalton here. And Dalton's kind of the father of modern atomic theory. And first got to say, well, what is modern atomic theory? Well, modern atomic theory proposes that all of matter is made up of little tiny particles that we call atoms. Hence it's called atomic theory. And so Dalton said that these little atoms, it turns out there's not just one type of atom, there are, 100 or 20, it turns out. He didn't know that yet, but we now know there's 120 or so different types of atoms. We call those different types elements from the periodic table here. So basically he went and said that the atoms of one element are different than the atoms of all the other elements. That's another part of his atomic theory. And then he said that we make up compounds by combining atoms of different elements. So finally, he said that atoms are not created or destroyed in a chemical reaction. So they're just going to be rearranged in different combinations to make different compounds and stuff like this. So that is Dalton's modern atomic theory. And then these other 3 here all made contributions to the structure of that atom. Now, we now know that at the center of an atom is a nucleus, and we know in that nucleus there are going to be protons and neutrons. Now the protons, which I'll abbreviate with the letter P, are positively charged, it turns out, and the neutrons are neutral, hence the name neutron for neutral. So, and it turns out this is almost where all the mass of an atom is concentrated at that center, and then floating around, and I'll say floating around, I don't know if that's really a great technical way to describe it, but floating around there are going to be some little teeny tiny electrons that are much, much, much smaller than the nucleus here and much smaller than the protons and neutrons of the nucleus and weigh a whole lot less. So to get a kind of an idea of the scale of things here, so these are super tiny first off. So like we're talking a fraction of a nanometer for most atoms. They're just super tiny. So, but almost all the mass is concentrated in the nucleus, but almost all the volume is in what we call this electron cloud on the outside. And so to give you kind of some of the scale here, so say we look at the nucleus and we were able to, blow it up to the size of a basketball. This electron cloud would probably be a few miles big with little tiny marbles going around it. And so most of an atom is actually made up of empty space. And this is kind of mind-boggling because, most of the universe, if you, kind of go around out in space and stuff, is made up of empty space. But then it turns out even when you encounter matter, which is all made up of atoms, according to modern atomic theory, even the atoms themselves are made up of mostly empty space. And again, this is kind of mind-boggling. And so this is kind of one of the representations we commonly draw. But keep in mind, this electron is just kind of going around and zig and zag, and it's actually even more complicated than that. It's got some wave-like behavior we'll find out later on. So, but these are your big 3 subatomic particles. You got protons, neutrons, in the nucleus, and then electrons going around. Again, protons are positive, electrons are negative, neutrons are neutral. And these other 3 guys made contributions here in each of these. So first we got J.J. Thompson. So J.J. Thompson, he's the guy that discovered the electron. And it turns out he discovered a little more about it. He discovered the mass to charge ratio. He didn't know the mass or the charge, but he knew the ratio of the mass to the charge of that electron. But you probably suffice to say, if you know he discovered the electron, you're good to go. Now, Robert Millikan is the guy that came next, and he built on Thompson's discovery of the electron, and he actually was able to figure out both the mass and the charge. And the truth is, he just figured out, the charge of the electron, and then was able to actually then, based on knowing Thompson's mass-to-charge ratio, then he could calculate the charge of the electron. The mass of the electron. And so you should know that Millikan here built on Thompson's discovery and basically figured out the mass and the charge of that electron. And then finally, we've got Ernest Rutherford. So Ernest Rutherford kind of gives us our modern picture of the atom with this highly concentrated center of mass here called the nucleus. So we didn't always know this. So somebody came along with what's called the plum pudding model, which is just kind of this, the atoms were just this kind of soupy mess of protons, neutrons, and electrons and things of this sort. So, well, what Ernest Rutherford did is he took a super thin piece of gold foil and he shined what are called alpha particles at it, which are super tiny particles that are the equivalent of a helium, looking at the wrong place, helium nucleus. So, and he shot a ray of these at this gold foil. And if these had been kind of this solid plum pudding, we'd expect that all of them would get reflected back or scattered off to the side and stuff like this. But what he found is that when he shot this ray of alpha particles at this thin gold foil, that most of them just passed right through the gold foil. And that was shocking. And that's what told him that most of an atom was made up of mostly empty space. So think of like shooting a beam of sand right through like a volleyball net. Most of those sand grains are going to pass right through and not contact the net at all. So what he did find though is that every once in a while, some of those grains of sand, in this case alpha particles, were reflected backward or at least scattered off to the side. So what he figured out is that there must be some really dense mass that's not taking up most of the volume, but concentrated. And that's where he came up with this nuclear idea, where most of the mass of an atom is actually all in this little tiny nucleus right at the center of the atom. So, and that's Ernest Rutherford. So you should know that he kind of did the alpha particles at gold foil experiment, and he discovered the nucleus, so to speak. So those are your fathers of modern atomic theory, and you should kind of, again, just have a little tiny description. So if you're looking at the study guide, it's all kind of there for you outlined in a table. Now I want to talk a little more about the protons, neutrons, and electrons here for just a second. So let's get our fathers of atomic theory out of here. So if we take a look here, so your proton, we say it has a +1 charge. And the electron, we say, has a -1 charge. Well, we're kind of taking this a little tongue-in-cheek here. So +1 and -1, basically because this is like the fundamental charge. If you have a +2, +3, +4, it just means you have either, extra protons if you're positive or extra electrons if you're negative or something along these lines. There's an imbalance there, but this is what we call the fundamental unit of charge. But we don't actually measure charge in this simplistic +1 and -1 units. We actually use what's called the coulomb. And so it turns out this electron has a charge of -1.602 times 10 to the -19 coulombs, whereas the proton is positive 1.602 times 10 to the -19 coulombs. And so when we say something has a +1 charge, what we really mean is that it has this value of charge in coulombs. We have to say that something has a -1 charge, we mean that it has this value of charge in coulombs. And so if something was +2, it would be double this value. -2, double this value. +3, triple this value. -3, triple this value. So, and the thing is that this number is actually fairly important in a physics class. But in general chemistry here, you may never see this number again in this course. And from here on out, we're probably just going to start saying +1 and -1 and just kind of know that it means this value or this value and just kind of allude to it. But when we say +1, +2, +3, we're not using an actual charge measurement in coulombs. We're just measuring it in terms of what we call that fundamental charge. So and it turns out this is the fundamental charge. Everything that's charged in nature is some multiple of one of these numbers, depending if it's positive or negative. So that's kind of the deal. It turns out that your proton and your neutron both weigh approximately 1 AMU, and this is new. This is what we call an atomic mass unit. These are so small that measuring them like in grams is not the most convenient thing. And so a neutron, once again, also approximately 1 AMU. And they're in a table on the study guide here. And it turns out the neutron is just slightly heavier than the proton. If you look there, neutron 1.00867 AMUs, proton 1.07, should be 00728 AMUs. So I'll have to add a 0 back there before you see it. Cool, and so they both weigh about 1 AMU, whereas the electron weighs like 1/1841th or 1/2000th essentially of an AMU, so about 2,000 times less than either a proton or neutron. So electrons are much, much, much smaller than either those protons or neutrons. And those numbers you don't have to memorize. I just want you to realize that about 1 AMU for the protons and neutrons, and if you had to round it to a whole number, the electrons would weigh about 0 AMUs, because it's like 0.0005 AMUs, something along those lines. So just kind of give you some relative sizes of these three particles. Now, going on from there, we want to talk about isotope symbols. Okay, so this is what an isotope symbol looks like, and there's three characteristic numbers associated with an isotope here, and the first one down here in blue is what we call the atomic number. And it turns out the atomic number is the number of protons in the nucleus. So it turns out oxygen here, and this is the chemical symbol for oxygen, has 8 protons in the nucleus. And it turns out that number of protons in the atomic number defines what elements you have. And so if you look at a normal periodic table here, there's oxygen and there's the atomic number right above it. This atomic number is 8, which means that all oxygen atoms have 8 protons in its nucleus. If you look at nitrogen right next door, all nitrogen atoms have 7 protons in their nucleus. Carbon right next to it, all carbon atoms have 6 protons in their nucleus. That's what the atomic number always, always, always tells you. Now the top number here we call the mass number. So, and it turns out one thing that can vary is how many neutrons are in the nucleus. Now, if I have an oxygen nucleus, it will have 8 protons in it. But it turns out it could have some variable number of neutrons. So it turns out not all the atoms of an element are exactly alike. They will all have the same number of protons, but it turns out some of them might have a different number of neutrons. Now, in the case of oxygen, the most common isotope is oxygen 16. And it doesn't weigh exactly 16, but it weighs close to 16. And what you find out is that if you look at that mass number, you can kind of view that number as being in AMUs as an approximate whole number. It'd be close to like 15.999 something or other AMUs if you actually looked at the exact mass, but it rounds up to a nice whole number of 16. And what's nice is you can figure out, based on the atomic number and the mass number, you can figure out how many protons and how many neutrons. And so again, the atomic number gives you the number of protons, so we know that there's 8 protons. So, but in this case, it turns out that the mass number essentially is going to give you the combination of protons plus neutrons, since they both weigh about 1 AMU and the electrons weigh close to 0 AMUs. And so if you want to find out, the total weight, you just add up the protons and neutrons together because they contribute 1 AMU each. And so in this case, well, we know 8 out of the 16 are protons from the atomic number. So the other 8 out of 16, essentially you can just take and subtract the difference here, and 16 minus 8 gets you that there's 8 neutrons. And it turns out that's not the only isotope of oxygen. It turns out it's the most common, most abundant in nature, but it turns out there's something also called oxygen 18. And it turns out the only difference is that oxygen 18 has 10 neutrons instead of 8. It still has 8 protons, but with 10 neutrons, it would have a mass number of 18 instead. Cool, and then we've also got over here this lovely charge. And the charge means there's an imbalance between protons and electrons. Again, recall neutrons are neutral, but the things that are positive and negative are the protons and the electrons. And if you have a charge, it means those numbers aren't equal. And so in this case, with a negative charge, we must have excess electrons, more electrons than protons. And again, we can't change the number of protons. If this is oxygen, that's atomic number 8, and he's going to have 8 protons, period. And so when you have a charge, it turns out that atoms can lose and gain electrons. And so in this case, if you have a negative charge, you need to add some electrons to figure out how many you have. In this case, since we know we have 8 protons, well, we have 2 more electrons than protons, so we must have 10 electrons. If we had a positive charge, then we would lose some electrons to get that number. So if this had been oxygen plus 2, well, then that would have been 6 electrons instead. And if there was no charge written here, you just imply that that's neutral, and then therefore the number of protons and electrons must be equal, and that would have been 8 electrons in this case to match up with that atomic number. Now it turns out when you have a neutral atom, we call it an atom. Now when it has a charge though, like this one does, those get names, and we call those ions. And it turns out there's 2 fundamental types of ions, positively charged ions and negatively charged ions. So, and we have names for both of those. The positively charged ions are called cations. The negatively charged ions are called anions. So, and that'll become important later in this chapter. So, again, if your atoms are neutral and have no excess charge, we just call them atoms. But once they have an excess charge, either positive or negative, they're called ions, either cations or anions more specifically. All right, now we're going to briefly talk about what's known as the atomic weight or atomic mass. And the atomic weight or atomic mass is also published on the periodic table for you. Like for oxygen here, we see it's 15.9994. So, and it turns out that this number is different than the mass number we saw over here, which is rounded to the nearest whole number for 1. But also it turns out that this mass number corresponds to one individual isotope, Whereas this number right here is an average of the masses of all the naturally occurring isotopes. So if you look at, we said that in addition to oxygen 16, there's also oxygen 18. And these are the two most abundant isotopes, but it turns out there's way more 16 than 18. However, let's just pretend for a minute that there had been 50% 16, 50% 18, and then we took the average mass, and that average mass would come out to 17. And so we'd expect a number to be, somewhere right around 17. Well, it's not. It's right around 16. And the reason it's right around 16 at 15.9994 is that almost all of the naturally occurring oxygen is actually oxygen 16. There is not a lot of oxygen 18 out there. So over 99% is oxygen 16, less than 1% is oxygen 18, and that's why when we take an average, and in this case we'd have to take what's called a weighted average, which weights the thing that's more prevalent or more abundant more heavily, that's why the average comes out really close to 16 for that atomic weight or atomic mass for oxygen. So again, I want you to see the difference between the atomic mass posted on the periodic table and the mass number of individual isotopes that you'll see in an isotope symbol. Now, if you look, for most elements, it's kind of like oxygen here, where you have one major isotope. So I might ask you, what's the major isotope for carbon? And if you said carbon-12, you'd be totally right. Roughly 99% of naturally occurring carbon is carbon-12. And if I said, what is the most abundant isotope for hydrogen? And if you said hydrogen-1, you'd be totally correct. And if I said, what's the most abundant isotope for helium? If you said helium-4, you'd be exactly right. And if I said, what's the most abundant isotope for bromine? And if you said 80, that's where you'd finally be wrong. So it turns out for bromine at 79.9, no bromine 80, turns out. So bromine's kind of an exception. So instead of having one major isotope, turns out bromine has two major isotopes. And they're bromine 79 and bromine 81. And it turns out it's almost exactly 50-50. And because it's almost exactly 50-50, that's why the average comes out almost exactly halfway in between at 80. It's almost like you just took 79 plus 81 and divided by 2, a normal kind of, arithmetic mean, an average. So it turns out it's just a slight excess of bromine 79. It's like 50.5% and 49.5%. And that's why it comes out a little closer to 79 than it does to 81. So, however, in the case of chlorine, things are going to get a little bit weird. If we look at chlorine, chlorine also has two major isotopes, not just one. And that's a good thing, because a lot of students look at this chlorine and they say, oh, it's like 35 and a half. This 35.4527, it's about 35 and a half. And they look at that and they think that that means isotope number oftentimes. And again, that's not what that means. You might be like, what would chlorine 35.5? If it had a mass number of 35.5, does that mean it has like an extra half of a neutron? So, and again, here's the key, is that most of these are really close to a whole number. So what happens when one is not? Well, again, that means that you don't have just one major isotope for sure in that case. And so in the case of chlorine, its two major isotopes, it turns out, are chlorine 35 and chlorine 37. And in this case, if we look at that average atomic mass, again, that atomic weight, it's 35.457. It's roughly 35 and a half. And we notice, well, that's closer to 35 than it is to 37. And that must be because we have more chlorine 35 in nature than chlorine 37. And that's totally true. So, and in fact, we're at around these numbers. We can get more exact numbers of these, but these will be good enough for us. 75% of the naturally occurring chlorine is chlorine 35. 25% of the naturally occurring chlorine is chlorine 37. And so that's why that average comes out closer to 35. And so you might actually be asked to calculate that average and come out with, something akin to this kind of a number. So, and they might do it, when you don't have a periodic table handy so you can't look it up, or they might invent an element that's unknown in our universe or something like that, and just make up numbers that way, because you're almost always gonna have a periodic table in front of you, so they don't want you to be able to just look up the answer and not do the calculation. So just keep that in mind. Also note that they're not just going to leave you with nice rounded numbers. It turns out like the 75% is actually like 77%, and this 77.6% or something like that, and this 25% is like 22 point something or other, and and then also this 35 and 37, it's not exactly 35 AMUs and 37 AMUs, these atomic mass units. It turns out these are rounded to the nearest whole numbers, and they might give you like 35.01463 AMUs and 37.00642 AMUs, and give you exact numbers. So, and again, I'm leaving out the exact numbers because I think that just makes this a little too cluttered, and we can learn the process without those. So how do we take a weighted average here and come out with this number that's akin to something around 35 and a half here? what you do is you take the decimal form of that percentage, 0.75. Let's do this in black. And then multiply by that corresponding weight, in this case 35 AMUs, and then add it to this guy here. So abundance is 25%, so 0.25, the decimal form of that percentage, times 37. And that's it, actually. That's the entire calculation. So you multiply the relative abundance as a decimal times the corresponding mass in AMUs, and then add them together. And so in this case, this comes out to exactly 35.5 AMUs. And again, it doesn't come out to 35.4527 because I've rounded the numbers. I haven't given you the exact masses in AMUs to so many decimal places, and I haven't actually given you the exact percentage abundances either. I've rounded those as well. So, but had I given you more exact numbers, it would have actually come out exactly to 35.4527. So cool, and this is how this works out. And if you kind of look at the way, the reason this works out this way, let's just say we had 75 dogs that weighed 35 kilograms, and we had 25 dogs that weighed 37 kilograms. And then we said, well, what's the average weight of all our dogs? So normally what we do is we add up all the weights of all those dogs together and then divide by the number of dogs. And we could do that. So notice we could take the 75 dogs that weigh 35 kilograms, plus the 25 dogs that weigh 37 kilograms, and that would get us the total weight of all the dogs. And then to turn that into an average weight, we divide by the total number of dogs. And it would look like this. So that's akin to what we just did right here, because dividing these two terms which are added together by 100 is no different than splitting these up into separate terms that are each divided by 100. But I could take that 100 there and divide it through by either one of these. And what if I just choose to make it the 75? And 75 divided by 100 is 0.75. And 25 divided by 100 is 0.25. And we get exactly the same formula we just had a second ago. Cool, and again, this is a process you're probably going to have to know for your exam, so you're going to want to get good at calculating these atomic weights being provided with these relative abundances. All right, so let's take a closer look at our periodic table here. And we've got, again, roughly 120 elements, and there's some debate sometimes on, did they really discover these? Not. This periodic table is a little bit old right now, but usually the modern ones have it filled in all the way to 120, FYI. And if you look here, there's a couple different ways we can divide this up. Now, one, you should know that we talk about groups and periods, and the groups are the columns and the periods are the rows. Now, the reason the columns are called groups is that we group together things that have similar properties, and that could be both physical and chemical properties. And so it turns out, like if I said, find somebody who has similar chemical reactivity to fluorine here, well, then you'd probably better off picking either chlorine, bromine, or iodine, somebody in the same group. And so that's the kind of question you might see, is just finding somebody of similar chemical or physical properties, probably picking somebody in the same group. All right, now periods, it turns out, so the periods are the rows, and if you think of something that's periodic, like the sun rising, every 24 hours, sun rises, every 24 hours, sun rises, it's periodic, it happens periodically. Well, same thing here, as you make your way across the periodic table, so let's say we go to our first, what we call noble gas right here, this column right here, this group we'll call it, they're called the noble gases, and it turns out their chemical reactivity is very similar in the idea that they're not chemically reactive at all. We call them chemically inert. And so it turns out as you make your way across the periodic table, boom, you run into somebody who's chemically inert. And then you make your way across again, and boom, you run into somebody that's chemically inert. And you make your way across down the road, and boom, you run into somebody that's chemically inert. And you're just periodically going to run across something that has that same chemical property, in this case being chemically inert. And that's what makes this the periodic tables. And as you make your way across a period, you're going to encounter an element of similar chemical nature at the same place in the next period is typically the way that works. So that's why we got, rows that correspond to periods and columns that correspond to groups, and you should understand that. You should also know that we have two big divisions in the periodic table. A lot of periodic tables will put like a little staircase right along here, even to kind of make it more obvious. This one doesn't. So, but right along that staircase, it turns out everything on this side of the staircase, down here and everything, these are all metals, and everything up here is non-metals. And so those are your two major types of elements, metals and non-metals. And I say the two major types, there is a third type, but it's a fairly minor type. And it turns out that right along that staircase here, like silicon and germanium and arsenic and stuff like that, that is what we call the semi-metals or metalloids. So, and there's only like 5 of them. So left side of the staircase, all the metals. And notice we have way more metals than anything else. Right side of the staircase, non-metals, and then right in the middle there's a handful of what we call semi-metals, which have some properties of metals and some properties of non-metals, are kind of intermediate, hence the name either semi-metals or metalloids. So you should be able to identify whether, if I say argon, what is it? Metal or non-metal or metalloid? You should be, oh, that's a non-metal. And if I say, nickel, what is it? You should say metal. So we got that division now down. There's also 4 groups that you should know the name of. So it turns out it's group 1 here, the first column, group 2. So, and then way over here, group 7 and group 8, which some people call 17 or 18, depending on how these go. But sometimes you'll just see group 1, 2, 3, 4, 5, 6, 7, 8, or sometimes they'll number them all. And there's a couple different numbering systems usually designated A or B. I don't care about that, but I do care that you know the names of 4 of those groups. And these group 1 elements right here are called the alkali metals. Alkali metals. Let's write that down. All right, so that's the alkali metals here. We got lithium, sodium, potassium, rubidium, cesium, and then francium is really radioactive and people don't play with it a lot, but it technically is an alkali metal. So, and then it turns out the group 2 elements right next to them are called the alkaline earth metals. Later on, we'll learn some of the chemical properties of these, and turns out these metals are really reactive with water. In fact, if you look at like sodium on down here in the alkali metals, they're explosively reactive with water. And we don't normally think of metals as reacting with water, but they are. And we'll learn about that when we get to chapter 7 in a little more detail here. The alkaline earth metals are also somewhat reactive with water, but not in general as reactive as the alkali metals. The other 2 groups we've got to know are the last 2 here, and group 7 here are called the halogens. And that includes fluorine, chlorine, bromine, and iodine here. So, and then finally the last one we kind of hinted towards as well, which is helium, neon, argon, krypton, xenon, radon, and those are the noble gases. And again, they're known for being chemically inert, which we will once again learn a little more about, or actually just rehash that in chapter 7. Some of the others have names here as well, like oxygen's group here is called the chalcogens, but not usually something we put you on the hook for. There's also a couple other things you should know. So right in the middle of the table, right in between here and here roughly, these are called the transition metals that are indicated on your study guide, the transition metals. And technically, whether or not the last couple here are considered transition metals, they're technically not, but you're never going to learn that as a freshman in general chemistry. So, but these are the transition metals in kind of general. So, and then way down at the bottom here, and you can kind of see it written here, this is the lanthanides and the actinides as well. So sometimes called the heavy metals, or at least some of the heavy metals, because technically some of these are considered heavy metals down here as well. But cool, those are the divisions you kind of got to know. And again, we've identified metals versus non-metals versus metalloids. We've identified 4 of the groups. We've got the alkali metals, the alkaline earth metals, the halogens, and the noble gases, and then the transition metals. So, and then finally, lanthanides and actinides, I'm not super concerned there, but that will come up a time or two, especially later on in the course. And that's it for our introduction to the periodic table. If you have found this lesson helpful, please like and share. Let's YouTube know that they should show this to other students because they're going to find it helpful as well. If you got questions on anything we've covered, feel free to leave them in the comment section below. And finally, check out my premium general chemistry master course at chadsprep.com. I'll leave the exact link in the description. In addition to the videos and the study guides, I've got over 1,200 practice questions, final exam rapid reviews, and practice final exams for general chemistry. Best thing is there's a free trial available, and everything in chapters 1 and 2 is included as part of that free trial. Happy studying.